Hey there, and welcome to This Explainer. If you've got your Secondary 1 Transportation Science Physics exam coming up and you're feeling a little overwhelmed, take a deep breath. I'm here to act as your study buddy to help you ace it. We're going to distill all those textbook pages into exactly what you need to know, focusing heavily on the key physics formulas, core definitions, and exactly how energy interacts in the real world.
So we don't get totally overwhelmed, we're going to tackle this in a structured 4-day intensive plan. Core stores, transfers and work, formulas in action, and finally, a quiz to really test your knowledge. Let's jump right in.
Day 1, Core Energy Stores. We absolutely have to nail down our foundational physics vocabulary, so the rest of this makes perfect sense.
Okay, the absolute most crucial concept you need to memorize right now is the strict scientific definition of energy. Energy is simply defined as the ability to do work. Seriously, whether you're lifting a heavy box or just flipping on the TV, you need energy to make that happen. And remember, we measure both energy and work using the standard SI unit known as the joule. That's represented by a capital J. Keep that J in mind because you're going to be using it a lot.
All right, let's categorize these different energy stores. A really great mnemonic to remember them is kids go everywhere carrying new ideas. That stands for kinetic, gravitational, elastic, chemical, nuclear, and internal. So moving objects use kinetic. Raised objects, like a waterfall, use gravitational. Stretched things like rubber bands hold elastic potential. Chemical covers fuels, like petrol, coal, or even the firewood you burn. Nuclear comes from atomic interactions. And internal energy, well, that's just the total heat and particle movement hidden inside any system.
Moving right along to Day 2, transfers and work. You see, energy doesn't just sit there doing nothing, it's highly dynamic. Let's look at how it actually moves. You absolutely must memorize these 4 specific pathways because they are literally the only ways energy can travel from one object to another. First up, energy transfers mechanically. This happens when a force acts over a distance, like pushing a heavy cart. Second, electrically, via an electric current traveling through wires. Third, by heating. This is always driven by a strict temperature difference, naturally moving from hotter objects to colder ones. And fourth, by radiation, which involves the propagation of waves. A perfect real-world example of this is how the sun transfers energy to Earth through light and infrared waves.
Understanding what happens during these transfers is super vital, especially in everyday household electrical devices. Let's say a television takes in a total energy input of 900 joules electrically, but it only outputs 800 joules of useful energy like light and sound. So where did the rest go? Well, those missing 100 joules didn't just vanish into thin air. They dissipated into the surrounding internal store via heating. This is exactly why your appliances get warm when you leave them on for a while.
And that brings us to the absolute golden rule of physics, the principle of conservation of energy. This principle states that energy cannot be created or destroyed. It can only be transferred from one store to another. You can think of it kind of like a closed bank account. The currency, which in this case are our joules, just changes forms or moves between different accounts, but the total balance always stays exactly the same. The total energy input is always going to equal the total energy output. Now let's clear up one of the trickiest definitions in physics, work. For work to actually be done, a force must move an object in the direction of that applied force. If you apply a 50-Newton force to lift your heavy bag onto a shelf, you're doing work. But imagine leaning back and pushing as hard as you possibly can against the solid brick wall. You're going to get exhausted, right? But in physics, work equals force times distance. Pushing a stationary wall means 0 distance, and anything multiplied by 0 is 0. No distance means absolutely no work.
Welcome to Day 3, Formulas in Action. Let's roll up our sleeves, because this is where you're going to score the big points on your exam.
Before you even think about touching a calculator during the test, follow these key steps to identify your variables and avoid those frustrating, careless mistakes. First, identify your mass, represented by a lowercase m. Second, identify your height, h, or velocity, v, depending on what the problem is asking. And third, always note the gravitational field strength. Unless the problem states otherwise, g on Earth is a constant 10 newtons per kilogram. Seriously, write these down at the very top of your paper.
All right, so our first major formula is for gravitational potential energy, or EP. An object's energy here depends entirely on 3 things: its mass, the Earth's gravity, and its vertical height from its previous position. The formula is beautifully simple. EP equals m times g times h. Let's look at a classic exam practice example using a block on a slope. If you push an 800-gram block up a ramp, examiners love to try and trick you with extra numbers. To calculate its gravitational potential energy at the top, you only use the straight vertical 3.0-meter height. Do not use the 5.0-meter diagonal distance. Also, remember our mass variable? You absolutely have to convert those 800 grams into 0.8 kilograms before you multiply anything. So the math would be 0.8 kilograms times 10 for gravity, times 3.0 meters for height.
Now let's see this in a real-world transportation system. When a roller coaster is just resting at the top of a hill at point A, it has maximum gravitational energy. As it drops down the track to the bottom at point B, that gravitational energy transfers mechanically into kinetic energy. Remember, kinetic energy relies on velocity, and the formula is 1/2 mass times velocity squared. So as the height hits zero at the bottom of the drop, the velocity and the kinetic energy hit their absolute maximum.
And we've made it to day 4, traps and quiz. It's time to test your knowledge and help you avoid the pitfalls that cost students the most points.
Here's your essential checklist of top study tips and traps to avoid when you're solving energy problems. Trap number 1, just like we discussed, forgetting to convert grams to kilograms. Trap 2, using a diagonal sloped distance instead of the straight vertical height for gravitational potential energy. And for my top study tips, tattoo that G=10 constant in your brain. And always, always write your final answer with the standard unit J for joules. Remember, a naked number is a wrong number in physics.
Okay, let's do a rapid-fire true or false review to check your understanding of these core definitions. Question 1. True or false? All moving objects have energy in their kinetic store. Take a quick second to lock in your answer.
The answer is true. Because the formula for kinetic energy relies directly on an object's velocity, this means anything that is moving, whether it's a massive rocket launching into space or a tiny ant crawling on the ground, has energy in its kinetic store.
Moving to question 2, true or false? Energy is destroyed when it is dissipated from a household electrical appliance, kind of like our TV set example from earlier.
That is false. Remember our bank account analogy? The principle of conservation of energy guarantees that this energy cannot be destroyed. It's simply moved to the internal store of the surroundings by heating. That's exactly why we call it dissipated energy rather than destroyed energy.
All right, here's our final true or false question, testing that really strict scientific definition. True or false, work is done if you apply a massive exhausting force to a heavy stationary rock.
False again. It's a classic physics trick question. No matter how much you sweat or how hard you push, if that rock doesn't budge, the distance moved is 0. And force multiplied by 0 distance means exactly 0 joules of work is done.
Wow, you've done a fantastic job running through these concepts today. I want to leave you with this really provocative thought straight from your exam notes to ponder. Since the principle of conservation states that energy cannot ever be created or destroyed, does that mean the energy making your muscles move right now and the energy powering the screen you're looking at has essentially lasted forever, just changing forms over and over since the very beginning of the universe? Pretty mind-blowing, right? Think about that as you finish studying. You're going to do great. Good luck on your exam.